This video is entitled The F-Distribution in One-Way ANOVA. ANOVA stands for Analysis of Variance. Now, we have not used the F-distribution and other applications comparing two variances. You can do hypothesis testing comparing two variances. So let me introduce the F-distribution because we're going to need that to use with our ANOVA. So let's just kind of briefly take a look at this. And let's see. This is when you're comparing two different populations. So S1 and S2 are the variances for two populations, and they're assuming that the population variances are equal. And F is essentially a ratio of S1 squared over S2 squared, the first variance divided by the second variance. Now, the F distribution, similar to the T distribution, is that it's a family of curves, except there's some obvious differences here. Everything's going to be positive for the F distribution. There won't be plus and minus critical values. It's all positive. And the F distribution is actually based on two different degrees of freedom, called degrees of freedom numerator and degrees of freedom denominator. So that's how you will use the chart when you're looking up that here shortly. So F distributions are positively skewed, meaning right skewed. And just like the normal distribution, the T distribution, the total area under the curve equals to 1. And number 4 is what I was saying, where they're positive values. And I wouldn't worry about number 5. The mean value is always 1. All right, so you see it's a variety. There's a different, shapes of graphs based on the different degrees of freedom. So the critical value that we'll be looking for when we do our ANOVA test is going to be the critical value F, such that your level of significance alpha would be the area to the right of that. And with standard hypothesis testing, rejection ideas, critical regions, if your test statistic F falls in the region greater than your critical value, it's strictly going to be greater here. There's no two-tailed things or anything. So if it's greater than, you're going to reject the null hypothesis. So this is just practice of looking up the chart here. So an F curve has degrees of freedom of 8, 15. So 8 is the numerator degrees of freedom. 15 is the denominator. Find the F value having area 0.05 to the right. So let's take a look at our F chart. So you can see here, zoom in on this a little bit. Your alpha is in the top row. So obviously anything we use is going to come from this chart. I think we have 5 pages of this. I believe 0.10 is the largest, yes. So here you got to find the correct alpha. So here's 0.05. And actually, in a lot of ways, this is, you can make a case for this being easier to read than the T distribution because you don't have to worry about one-tailed or two-tailed. All you have to do is find the right alpha, and then you're looking at two different degrees of freedom. So it was 8 and 15, I believe. Go back over there and look. I should have it sort of snipped out of there. But degrees of freedom numerator right here is the 8. 15 down here. Let's see if I can highlight that. Hopefully you can see my arrow pointing right at it, but I'm moving the cursor around. But there it is on row 15, your denominator degrees of freedom. And where'd it go? Right there. Yeah, 2.64. So let's see what I can see. 2.64 checked. And now I have a little snippet from the table there. Obviously nothing. We just looked at the entire table. But there's the 0.05, and you see there's the 8 degrees of freedom numerator. 15 denominator, there it is, circled, 2.64. So I don't think that's too bad. Here's one that says F curve, degrees of freedom 6, 20, with an F value area of 0.10 to the right. So in other words, that would be the same thing as saying, alpha equals 0.10. That automatically implies area to the right for this graph. So there's no other wording there. But it could have said find the F value for alpha equals 0.10, and that would have been the exact same process. So I could go to that F table I just showed you, but I'll just take the little snippet right here. Well, we've already shown you there's like pages of the F table. So here's the degrees of freedom numerator across the top. There's 6. Come down here. Here's 20. 6 meets 20. 2.09. And there's the answer, 2.09. Well, okay, so long as we don't confuse I think the numerator and the denominator degrees of freedom, this should be okay. And then, of course, also make sure we're looking at the correct alpha. Now, one-way analysis of variance is a hypothesis testing technique. It's interesting that it's called variance, but you're actually testing means, equality of means. Now, it's generally defined for 3 or more populations. It can be done for two populations, comparing 2 groups, but there's other processes, a T process that can be used for 2 groups. So we're going to focus at 3 or more, but it could be done for just 2 means. It's not mathematically impossible, but this is where it requires the F if it's more than 2. So Anova, there in all caps, is the abbreviation for analysis of variance. Now the null hypotheses for these are real straightforward, not too bad. It's always equal. So it's whether it's 3 or more groups, the null hypothesis would be mu1 equals mu2 equals mu3 equals however many means there are. You're saying they're equal. And then the alternative would be at least one mean is different from the other. So so when you reject the null, you're concluding that at least one of the means is different. Now it says without performing more statistical tests, you can't determine which of the means is different. For example, let's say if you had 5 groups, and you rejected they were all equal. Maybe based on the sample data, you could possibly take an estimate at which one you think, or maybe it's more than one, but you thought, nah, this one looks off. You could actually throw it out and test the other 4, and then if you did not reject the null hypothesis with the other 4, then that was probably means it was that one particular group that was making you reject them being equal. So that's what it means by more statistical tests. You would kind of like remove, different one or more of the populations from here, and then you would run the Anova test again. So here are the basic criteria, basic process that you have to, conditions you have to follow. And it's not going to be any issue because we're going to always follow these conditions. Each sample is selected from a normal or approximately normal population. The samples are independent of each other. So one group's not influencing the other. Each population must have the same variance. An example of independent versus dependent. Independent means just one thing doesn't have an effect on the other. But an example of dependent group samples would be, let's say, if you took a population of people, let's say maybe and measured their resting heart rate, and you took the same group of people, and then they had them maybe be on a treadmill for 30 minutes or something. You measured their heart rate. That would actually be a dependent sample because it's not an independent group. It's measurements based on conditions applied to the same population. And then each population is just assumed to have the same variance, same population variance. And we have what's called the between samples and within samples, which all you're going to be doing is looking at an output here. So the test statistic is the variance between samples and then divided by the variance within samples. And then we have what's called the mean square between, which is where you take, the measured difference related to treatment given to each sample, and then the mean squares within measures the difference related to entries within the same sample. So between measures group to group, and then within measures within the group. And it says here the within is usually due to sampling error. So to calculate the, got away from me there, the F-test statistic is actually going to be the mean square between groups divided by the mean square within groups. Now here's how we measure the degrees of freedom. K represents the number of groups. So if you were testing 4 different populations being equal to each other, that's what K is. And so the degrees of freedom numerator would be K minus 1, so it would be 3 if there were 4 groups. And degrees of freedom, and here K is the number of samples, that's what I mean by groups. And then the degrees of freedom denominator is N minus K, where N is the sum of the sample sizes. And they can be equal sample sizes from each group, or they can be different. You'll see the examples I'm doing are going to be different sample sizes. They could be equal. But just for argument's sake, till we get down to an example, let's say that you had 4 groups, and each of them had 8 samples per group. N would be 32. It would be all of those added together. But like I said, they didn't have to all be 8, was my point. They could be 8, 7, 6, 5, and you would add those 4 numbers up, and that would be N. So here's what's called an Anova summary table. Now, one thing I've left out of here, and I'm not having students do this. It's too messy, and it's not worth it really. But I've left out all the, there are a lot of formulas that can be done manually, given the data, how to calculate all this stuff. We're not going to waste our time with that. We're just going to look at it from an output. We're going to use Excel, but there's lots of statistical packages in the social sciences. SPSS is a commonly used one or whatever. So I decided there's no point in making you kind of crank all this out necessarily by hand. Well, if I say by hand, you'd still be using a calculator, but too tedious, not worth. So it's going to come up with something called, like I said, there's a formula for that, so don't worry about it. You're just not seeing it. The sum of squares for between, sum of squares within, and then degrees of freedom numerator, degrees of freedom denominator. And you can see this mean squares here that's kind of messed up there. That's not a minus, it's equals. I don't know, maybe just it didn't, when I copied and pasted it didn't look. Let me see if I can draw that in there. That should be equal, just like the one below it. There we go. All right, let me save this. So that is equal. So yeah, I don't know why that. I'm sure that it wasn't wrong in the book that I copied it from, but it just didn't cut and paste properly. Well, anyway, the sum of squares between divided by degrees of freedom numerator gives you this value mean squares between, and then sum of squares divided by degrees of freedom denominator gives you what's called your mean squares within, right there, that ratio. And then the F-test statistic is the ratio of this MSB number divided by the MSW. Now, I said I wasn't going to make you do all these calculations individually, and I stand by that. But I do like these kind of problems where you're just kind of using this, and it's not difficult, but you're just trying to find missing pieces on this table. You're given enough information. It may not look like it, but you are. You're given enough information. Now, this is not showing total here on this thing, though. But total just means you're adding down the columns. You don't really need, you would not see total for mean squares sum within. Let me look, definitely not for F. Let me look ahead there. Yeah, you don't see a total for this would be blank and then this would be blank. But anyway, For sum of squares, you do. They show. So you're just trying to figure out what fits what here. So these have to add downward, and so that means I've got it written out here in just a second, but you'll see. So the difference, this spot within would have to be 540, and if the total degrees of freedom is 21 and the degrees of freedom within is 18, that means the degrees of freedom between would be 3. And then mean squares between, will be the 270 divided by that 3 that would go in there, which would be 90. And then within will be the 540 divided by the 18 would be 30. And we add those up. And then the F only has one value here. It's going to be the top mean squares divided by the bottom mean squares. Between divided by within, right there. So it's kind of interesting. So it does this ends up being 3.0, and I have and then I also did the critical value for this. So the critical value of 0.025. I don't know if I snip this one out. Let's see if I did. Yeah, I did. Okay, so we'll come down and look at that. But anyway, so here's what I was just kind of saying verbally. I wrote it out now for the first part. So 540 would be the missing number for the first one, and then 3 is the missing degrees of freedom. So 90 would be the top mean squares, but you take 270 divided by 3. Then you take 540 divided by 18 to give you 30. We have 90 divided by 30 equals 3. And so it would be 3.0. Now this was obviously set up where the numbers all worked beautifully. Don't always assume that's the case, but that's what basic calculators are. To divide easy. More decimal numbers and stuff. So, but let's see what the critical value would be for this. And let's see. Pause for a second. So let's get the critical value then. We now know the numerator degrees of freedom is 3. The denominator is 18. And it's from the 0.025 chart. And you see there's 3 numerator degrees of freedom, 18 denominator, 3.95. So that's where I got that number from. Right there. So let's take a look at now, jumping ahead just for a second here, but let's say we've been deciding whether or not we're going to reject, since this test statistic is not greater than that critical value 3.95, not greater than, we would fail to reject the null hypothesis of the means all being equal. And you recall that when you fail to reject, that doesn't mean you totally support it. You just don't, you don't have enough evidence to say it's wrong. So you just kind of go along with it there and say, okay, can't say you're wrong, but so this is just kind of a guideline summarizing the process here. But we're not going to do a lot of this. As far as definitely not the math, because we're going to have the output here. But so it's telling you obviously just the null and the alternative are going to be straightforward. It's either however many groups you have, it's going to be mu1 equals mu2 equals mu3 equals whatever, and the alternative is at least one of them is different. It's just telling you to identify what alpha is. It's telling you how to get the degrees of freedom. For the numerator, it's k minus 1. And for the denominator, it's n minus k. And then it's telling you to look up the value on that chart that was showing you that, which is a file I keep posted for students. So this is that's what they're calling the table 7 here. All right. And you come up with the F statistic, test statistic. Then, like I was saying for that last one, if the F statistic falls in the rejection region, which is to the right of that critical value, That's the rejection region. The test statistic falls in there, you reject. And here's why I put it in writing here that we're not going to worry about the actual formulas. And as far as taking an exam, you're not going to have to use Excel for the exam purposes. Now, I may have you, do that on a sort of separate homework type assignment, but so I won't worry about that now. I would include that in a separate video. But all you have to be concerned for testing purposes is just reading. I'm going to explain what I did here, just to show you, but no, do not worry about having to do this during an exam. You would be given the output. So this is just showing us, so suppose someone was testing this process with 3 different washing machines. We're testing that the claim is no different for the means and the machines. So you can see there's 3 different sample sizes here. So I put the data in Excel, and then a command called data analysis, which is an add-in. So it's a free add-in. But so if you look up in Excel, I'll go ahead and bring up Excel for a minute. I'm not going to redo the entire problem, but like I said, even though you're not going to have to do this, unless it's a separate assignment, then you would. So you might need to see this anyway. Let's leave that alone for a second. But anyway, the data's all here. And then I highlighted all those cells, including the empty ones. You highlight all of them because Excel will know to ignore the empty ones. Well, let me go to, after you add in, this is what you'd be looking for, is that data analysis right over there. That data analysis, if the add-in was not there, you wouldn't see that. But that has to be done for this command. And you click on it, like I said, even though I'm showing you this. And it's the very top one, Anova single factor. So that's what I was using there to do this. And so you select all the cells, including the blank ones. My data was in columns. I guess you could do it by rows. Now I'll show you another example here in a minute. If you actually, on the output, if you want to label, like if I would have put, let's say if I would have put in the top row of the output, machine 1, machine 2, machine 3, and then the numbers below it, I would have selected the labels, included the labels, and then checked this box labels in the first row. So that the program would know that the first row is not meant to be numerical and give you an error or something. So the alpha is 0.01, so I'll put that in there. And on the output, I don't put a range. I just pick a cell like E1, which would have been 2 more over to the right, like right here. So I would have started like right there. It doesn't matter. And it'll just go down and to the right. So you don't have to really tell it where to finish. It'll go down and to the right and won't overlap your original data. That's why I didn't put a final range there. So I come down here. So you see, it's without labels, it's just giving it generic names there. Column 1, column 2, column 3. And these are all the number stuff here that I said there were formulas for that I'm not going to show you how to do, nor do you have to worry about. All you care about is the Anova output down here. I just kind of highlighted some things. Now, one thing, the Anova that wasn't shown in those other Anova table examples that weren't from Excel is it didn't have the p-value. The p-value, just like for the t-distribution, really is too complicated to calculate. It needs technology. But we can still use the basic rules of hypothesis testing, and we can use the p-value to make our decision whether or not to reject. So I highlighted everything here, and it even gives you the critical value. But notice there must be some complicated math, to come up with that critical value. The chart only shows 2 decimals, which I'll show you. But it's using that based on these 2 degrees of freedom, 2 and 14. And let me mention real quick. So the 2 is coming from, there's 3 groups. 3 groups minus 1 is 2. And the 14 comes from, there's 17 total data values. 17 values minus 3 groups gives you 14 right there. In fact, I'll go to the chart right now. Did I show the chart? No, okay. I didn't snip it out this time, so let me just show it to you in real time here. I'm going to show you that critical value. So it's 214.01. Let's go 0.01. And degrees of freedom numerator is 2, so it's the second column. Hopefully you can see that arrow moving along there, pointing, and there's the 14. So it's right there, 6.51. So that is correct. Of course, Excel has it a much more sophisticated looking value there, doesn't it? 6.514, blah, blah, blah. Okay. But anyway, so it's spitting out that critical value. But obviously know how to find that critical value, because you still need to know how to do it, because let me scroll back up here, because it's very, very likely, I mean almost for sure, you would have a test question where you're just doing this, where you're just reading it off the chart. So, which isn't hard, but so don't think that this means you have to give up the ability to use that chart. So here's the F test statistic, which is actually the MS between divided by the MS within groups. So you took the top number divided by the bottom number. That would be the number here in yellow. So there's 2 ways to do this, just like we've always had before with hypothesis testing. If the F test statistic is greater than the critical value, we're going to reject. So the critical value is 6.51, blah, blah, blah. Here's the F, 7.103. So 7.103 is greater than 6.51. So we reject, and actually I'm including this in the same sentence as the p-value. So if recall from hypothesis testing that the p-value, if the p-value is less than your alpha, you reject. So I'm putting, both of these, it's got to lead the same conclusion. It's going to reject. F test statistic greater than the critical value, and the p-value of 0.074 is less than your alpha 0.01. That also means reject. So both of these mean reject. So it's going to reach the same answer. So you get reject either way. Oh, here's where I was explaining the degrees of freedom right down there. So, and there you go. So 2 ways. So that means we think, at least one of those washing machines times is not, average times is not equal to the others. So let's see what this is. Look at this one. It says 4 brands. It doesn't say what it's 4 brands of, the right topic, but who cares? That doesn't matter. So this time I did a little bit different, where I put the labels in there on purpose just so you could see it. So you see I wrote in brand A, brand B, brand C, brand D, put in all these values. So I went to Excel to run the Anova single factor again. And then you select that was A1, the up left. So you do include the label now. Go all the way down and just to whichever row has the last number there. It's okay for all those empty spots. That's fine. So I selected all that, also by columns. But now you can see I checked the box, labels in front row. First row. Well, okay, labels in first row. I put in my alpha. Be careful that the alpha, whatever's there might be for a different problem. 0.025, that was my alpha for this one. Output range, I started it in F this time, just 2 rows. Always like to leave a blank one there, so I started 2 over to the right. You'll see when it comes out, because it'll just print down and to the right. So let's see what we got here. So there is the, okay. Oh. Every time I moved down, it got away from me there. Went down a page and it took me back to the top. That's why I was confused. There we go. All right, here we go. There's all the individual information. But here are the key components we want here. The F-test statistic, the p-value, and the critical value. So this one, and so you see now it's labeled out, it's outputting them as brand A, B, C, D. So let's look at it both ways. The critical value is 3.95, which I didn't put the snippet from the table, but that'd be good practice for you if you want to go look that one up yourself and see if you can come up with. Obviously, it'll just be 3.95 on the table. But the F-test statistic of 0.05 is no way bigger than the critical value, so it's failed to reject. And then the p-value also should back that up, and it clearly does. The p-value of 0.98, that's a really high p-value. 0.98 is way larger than alpha 0.01. So to reject, it's got to be less than alpha. So we clearly fail to reject the null hypothesis that the means are all equal. And just, that obviously you don't have to, that's good enough, but I kind of, just want to show you this real quick. I mean, you still have to, look at these values to check everything, but notice that these means are all pretty close, aren't they? So I can just sort of logically see why we didn't reject. But that's not how you absolutely come to your conclusion. But yeah, they are pretty close, so surprised we didn't reject them. So as I'm mentioning, the actual idea of failing to reject doesn't mean we support it. It just means we don't have enough evidence to conclude that it's wrong. So we're basically kind of going along with it for the most part. So in this case, it certainly makes sense. So, well, all right, that concludes this video on the F-distribution and Anova.